Nasrin, you might want to go to full screen when it comes time to show your presentation. You know how to do that?
Yes, I think so.
There's right at the bottom of the screen there, where you had it, there's a little symbol. Where is it here? I think it's just before the size symbol there. I think that might, yes, that does it for you. Okay. Are you all set?
I think so.
Okay.
Yeah.
So I will start the proceedings underway. Good morning, everyone.
Good morning.
Good morning.
I'm Richard Langley, the newly installed or reinstalled from years ago Director of Graduate Studies in the Department of Geodesy and Geomatics Engineering. And we are convened this morning for the Master of Science in Engineering degree defense of Nasrin E.Ivari. The way that we'll run the proceedings, like usual, I will invite Nasrin to give a approximately 20-minute presentation of her thesis research. And then we will go to the questioning period. And I'll go through the questioners, the Board of Examiners in order as given on the notice of the oral. Monica, unfortunately, is not able to join us today, so I will ask her questions that she sent to me on her behalf. And so we'll have the usual 2 rounds of questioning, 3 questions from each of the examiners in turn, and then the possibility of a second round with 1 or 2 additional questions from each examiner. What else do I need to mention? Well, the title of the presentation is Data Stream Affinity Propagation for Clustering Indoor Space Localization Data. I think that might be it. Correct me, those that are more knowledgeable with the process, if I've omitted anything.
I think that's it.
Okay.
Just can I interrupt you?
Yes, you may.
Based on what we talked, my presentation is more than 20 minutes. It's around 30 to 35 minutes.
Okay.
Yeah, because my
longer than suggested for a master's presentation, even PhD, we suggest 25 to 30 minutes. But okay, we can't change the presentation in real time. So we better get started then. So I will turn it over to you, Nasrin. Others, perhaps, if you haven't done so, mute your mic, and we could even consider turning off your camera to save bandwidth. And then at the end of the presentation, I will invite the examiners to turn on their camera and microphones again. Okay, all set, Nasrin?
Yes.
On you go.
Thank you. Hello, everyone, and welcome to my presentation. Today, I'm going to talk about my research work on data stream clustering and introduce new algorithm for indoor localization data. During the presentation, I will go through the introduction of the subject and then the previous research work had been done. Also, I will talk about our method, then I will introduce 2 experiments we use, and next result, and finally conclusion and future work. What is data stream? Well, many systems generate observation continuously in real time. For example, infrared sensors used in indoor localization systems generate thousands of observations each second. For such a data stream, clustering and finding pattern is required because they are infinite and random access to data and storage are not possible. Stream clustering is an unsupervised machine learning technique, and there are different types of clustering methods are available. The Affinity Propagation Algorithm, or AP, has been chosen for this work. AP is a partitioning-based message passing algorithm, which means all data points are potentially cluster centers. And they send message between all data points to find the final cluster centroids. We have chosen AP because cluster centers of this algorithm are true representative of the location. Also, this algorithm doesn't require to specify the number of clusters before running the algorithm. Actually, this algorithm suffers from memory complexity, which it cannot handle a very large data set. Stream clustering is important in many indoor cases, such as to improve the management decisions, like to control the temperature of the building and where to install AC, for example. Another example can be advertising a product and where to install a billboard or a screen to have a higher viewers, and where is the most crowded spaces. A very important example in these days is to control the spread of COVID-19 in public places, such as malls and, for example, monitoring the human mobility to keep social distancing and keeps the limit number of people inside the spaces. For all this kind of application, finding a meaningful out of the infinite data is very important, and it's possible by a stream cluster analysis. Actually, we were faced two problems for clustering indoor localization data. First, the processing the fast incoming data, which is not possible to store and analyze all the data stream based on offline mode. So we had to solve the large scale issues. And the second challenge was related to data distribution due to the evolution of the clusters over the time. The goal of this research work was to develop the new data stream affinity propagation algorithm, or we call it DSAP, based on online and offline phases. Also apply landmark time window model to accumulate data points for generating macro clusters, and then evaluate the clustering result using the performance and validation metrics. And finally, show how well is DSAP for analyzing localization data stream for two experiments to find a staircase usage pattern and occupant behavior, both of them for indoor spaces. Previous research work shows that AP clustering algorithm is applied for finding clusters for Wi-Fi RSS at the university campus. There are few streaming AP algorithms exist, but none of them have been applied for clustering people counters and Wi-Fi localization data in indoor space. The first streaming AP algorithm is STRAP. This is online algorithm with using a sliding time window model. This algorithm starts with bunch of data and applying AP to compute the first centroids. As the data stream comes into the model, each data point is compared with the existing centroid. If it's too far from the nearest exemplar or centroid, it's put into the reservoir. Otherwise, the stream model is updated. This STRAP has two restart criteria. First, when the reserve oil it become full, and second, when the data distribution is changed. If these two happens, then the stream model needs to be rebuilt. In addition to STRAB, three more AP stream clustering algorithms exist. These algorithms were inspired by STRAB with some differences in update strategy. All these four models use a sliding time window. The first one, or the ISTRAB algorithm, has a mechanism to remove and eliminate outliers by using a standard deviation. But this is work well when we have just a normal distribution, and previous work showed that this is not a robust method for detecting outliers. The second ISTRAB is another algorithm introduced in 2018. This method has two types of judgment to update clusters, which are disappearance and reoccurrence. Actually, this method requires many parameters to be set from the user side. This algorithm has a high performance than STRAB, but it's not efficient in terms of time and memory. AP then stream is the only online-offline clustering method. This algorithm combines the STRAB with density-based method to find dense cluster. But this approach is computationally high, especially because of density decay function, and it has also used different type of data structures. The proposed method in this work is a simple version of all these algorithms. For example, the DSAB, or the proposed method, avoids the computation to detect reoccurrence and disappearance of cluster to avoid any extra cost. Also, we use a landmark window, which none of the previous work used this type of window. And I should mention that the programming code of this algorithm are not available except STRAB. Recently I found them. And due to all reasons, we propose data stream affinity propagation, or DSAP. The DSAP algorithm is based on online macro and offline macro clustering. The online macro detects the arriving data stream and update the cluster, and offline macro clustering is actually generates summary of all the clusters from centroid that's generated by macro clusters. Then the quality of clusters and the performance of the algorithm is assessed in the validation and evaluation phase. The online clustering phase is initialized upon receiving a sequence of data stream with landmark time window. In the landmark time window, all the data points in each window are equally important, and they have a same weight. As a new time window creates, all the data points from previous window are discarded. This window is suitable for our clustering method because first of its simplicity, and also we are interested in the most recent data points. The online macro phase has three main steps: initialization, comparison, and activate AP and update threshold. In the initialization step, the data points in the first window are clustered by using affinity propagation algorithm. And initial macro clusters with the centroids are generated in this step, and they are represented as a tuple of centroid of the clusters, the number of data points assigned to the cluster, and the last time stamp assigned to it. The mean of all intra-cluster distances give the initial threshold, give us the value of the initial threshold. And the intra-cluster distance means the Euclidean distance between each data point and the centroid. In the next comparison step, we want to find out if the new data point belongs to the existing cluster or not. To do this, we calculate the Euclidean distance between each data point and the current macrocluster. If the Euclidean distance of any data point to its closest centroid is less than the threshold, it is observed by the clusters, else it put into the time window repository. In the last step of the online phase, new macroclusters are aggregated and the threshold is updated. We apply AP algorithm on all data points that are temporarily accumulated in the time window repository to compute new macroclusters. These new clusters are added to the existing cluster. Because of a new cluster, we need to update the threshold. And to do this, first we compute the mean intra-cluster distances of new clusters, and then update the threshold by taking the average of the new clusters and the new threshold and the current threshold. And also to avoid the number of centroids grow beyond the control, all centroids that are no longer active should be removed. And this is done by keeping only the centroid that it's more than the time stamp, the expiration time. That when it's more than expiration time, then we can keep this kind of clusters. The expiration time also enables the algorithm to access the older data. I should mention that at the end, the online phase gives us a set of macroclusters which represent the current state of the stream. The offline phase gives us a final cluster from the aggregated summary data. In this phase, all the macroclusters generated during the online phase are reclustered by applying AP once again and generate a macrocluster. Intrinsic clustering validation uses the internal information of the clustering process to evaluate the goodness of the clustering. When we don't have ground truth of the data or we don't have the label. These metrics are first silhouette index, which is defined for each data point to measure how similar a data point is to its own cluster and compared to other clusters. Actually, this score is bounded between -1 and 1, and for example, -1 is for incorrect clusters and 1 is for highly dense cluster. The next index is Kolinsky-Harabat's score, which related to the model with a better defined cluster or well-separated clusters. This index is the ratio of the sum of between cluster dispersion and intercluster dispersion. And the last index is Davies-Bouldin index, which measures the average similarity of each cluster with its most similar cluster. I should mention all these indexes have a drawback, which are they are high for convex clusters, such as density-based clustering like DBSCAN. Then the performance of the DSAP is evaluated by time taken of the algorithm to run and the memory consumption. The DSAP implemented in Python programming language, and we use different libraries, for example, scikit multiflow, which is used to mimic the data stream and convert the collected data into the stream manner. The DSAP code is available freely in this link below, and I love to collaborate. DSAP was used to analyze data for 2 different indoor localization data. The goal of first experiment was to increase the physical activity of at work to reduce the health risks related to increasing the sedentary lifestyle. This experiment was conducted across 6 levels of the building at the Townsley building. It's in university in Australia over a period of 3 months to observe any behavioral changes in a staircase usage. The first month was used as a control month to observe the normal usage of the building. During the second month, motivational and educational intervention was done to encourage stair usage. And the motivation includes the screen that they are kept in close to the lift in the building, and to provide the health information and live feedbacks. For the last months, digital monitoring was continued to understand if any long-term change in the behavioral changes happen after the months of intervention. This study used people counter sensors placed on staircases. When someone passes, it counts. Finally, we use 2 features in time for cluster analysis, position and count. And I should mention that we use a 1-hour landmark time window. These 2 figures show the Townsley building inside and outside. The image on the left is the building overview from the north side, and the image on the right is the building plan for level 4, which stairs used for this experiment are highlighted in red dash circles. As you can see here, in this map, most all the classrooms are located in the south side. The second experiment, created at University of Jomah first in 2013, is a reference for W-line fingerprint-based indoor localization. We use this experiment to find occupancy behavior in indoor spaces. The measurement was done across 3 buildings. For this experiment, 18 participants with 16 phones measured their position and they move around the building. I should mention that we use 2 features in time for cluster analysis, phone and position identifier. Also, landmark time window of 10 minutes has been chosen for cluster analysis. In the results section, I will discuss the data from each experiment and the clustering result. This figure shows the stair usage pattern of people moving up and down. The first month or pre-intervention month is shown with the purple color. The intervention month is shown with the blue color. The white gap between a pre-intervention and intervention months was the 2 weeks of semester break, which we excluded from the study. The post-intervention or after intervention immediately start after the intervention month, and as shown here in yellow. As we expected, 15% more people use the stair to go down than go up. The 3 plots, this 3 plot actually shows the spatial temporal pattern of each level for each month. These are generated by aggregating the number of people at each level, and it's clear that level 2 to 1 stair was used most, and the north side stairs were used the least. This could be because of fewer people using the north entrance since it leads to the low capacity parking lot. Also, the peak of usage was around noon for all these 3 months. People have used the stair in the afternoon rather than in the morning. This DSAP algorithm is capable of analyzing the evolution of microcluster. The cluster of every hour of 1 day are shown here in these plots. These figures show the centroid of the microcluster and the data points that are connected using the straight lines. The 1 hour expiration time was chosen to see just the only data points in 1 hour window. The changes in stereo across all the levels can be clearly seen. The macro cluster shown an increase in activity around 9 at the peak around noon. That macro cluster become more dense and happening at a different level. Also, as the day passed, the number of microcluster gradually decreased. This generated pattern showed the potential using the DSAP for finding meaningful of microcluster over the time and space, and the ability to continuously find macroclusters with any changes in the data stream. The first week of each of these 3 months was selected to find weekly pattern and compare the result with the standard affinity propagation algorithm. The macro and macro cluster from DSAP are shown here, and the summary of the clusters are presented in the table. The expiration time equal to 168 hours was used. The macro cluster centroid are shown with the blue circles, centroid of the macro by red crosses, and gray dots are data points. The numbers of the data point also associated with each macrocluster are mentioned next to it. 5 macroclusters were found for each week, having a variety of different density. The trend of high density cluster with low count is present in this data. The microcluster level 4 to 3 south and 1 was selected during each month, as you can see here. During the first week of intervention, a very weak impact can be seen in stairs between level 2 to 3 north. The final clustering results for the 3 months are shown in this plot. The expiration time value is kept to the total of hours of the month. All the macro clusters for these 3 months are at level 2 to 1, 3 to 2, and 4 to 3 south, and 5 to 4 south, confirming that these levels saw the highest frequency of people. Also, 2 dense clusters with the number of data points equal to 53 and 25 were observed at level 4 to 3 south before intervention. And this cluster most probably correspond to the group of people using stairs during this month. And this behavior is not seen in the other 2 months. It's clear that during the intervention months, it gives us the most number of macrocluster. The densest cluster at level 3 to 2 represent around 30,000 data points during intervention, which the other months has dense cluster at level 5 to 4 south, and also before intervention is level 4 to 1. This level 5 to 4 south is the only state that keeps its behavior pattern similar to entire the 3 months. The people counter experiments was performed in order to find any improvement in stair usage after some measurement for educational intervention. There are no obvious actually signs for the overall increase in stair usage during, after, and during intervention. To compute the performance and validation metrics, the AP was used as a baseline. The micro cluster generated by DSAP show slightly improved values. Reduction in processing time and memory consumption is immediately apparent between the DSAP and AP. The initial value of the first window, actually the first window is the most time intensive step in this algorithm, but it performs only once and does not affect the current time window. The number of cluster of AP and macro cluster here are similar, which shown that DSAP generate consistent cluster. The DSAP indicate that they are used to evaluate the clusters. These indices actually used to evaluate the clusters and show that DSAP had a better result than AP. A stream clustering analysis for the second experiment was carried out to find out occupancy pattern in different buildings of the university campus. This experiment lasts for 6 days from May 30th to June 20th. But June 20th was selected for cluster analysis because significantly more data points were collected during these days. Figure on the right show an overview of the spatial distribution of the data points according to indoor spaces of these three buildings, which they are named as T1, TD, and TC. The first 5 days of the data was available from building T1, but on June 20, the data stream available for both building TD and TC. Also, the distribution of the data closely follow the shape of the buildings. This figure shows the spatial distribution over the floors. As you can see here, building TC is the only building with 5 floors. The total number of data points generated for each building is provided in this table, and it's you can see that building TC has contributed to 47% of the whole data. Data points gathered at different floors of all buildings are shown in this pie chart. The total number of data points gathered at different floors of all buildings was similar, except the 5th floor, which is belonged to just only one building. For the stream cluster analysis, the space and phone identifier are used. Space ID is a unique ID which represents the indoor spaces like classroom, labs, or offices that participants were occupying during the experiment. A space ID has a number ranging from 0 to 732 for all these three buildings. A space ID from 0 to 255 belong to building T1. A number between 256 to 460 belong to TD, and the rest of it belong to the third building. The figure on the right is the histogram of the data collected by 18 phone used by these participants, and the participant with the phone number 8 and 9 generate the most data during this experiment. It is important that the algorithm is able to find a representative macro cluster that reflect the changes in occupants' behavior. This evolutionary process can be seen in these figures, which is between 9:15 to 10:25 on June 20th. A 10 minutes time window and expiration time of 1 window was used to generate this plot. And these patterns show that 2 or more users rarely occupy the same indoor spaces. They also show how the macro cluster provide an overview of the movement in the building. So these plots show the strength of DSAP to detect and track people occupancy over a short period of time, which is in this example is 80 minutes. The DSAP clustering results for the day June 20 are presented in these plots. The first plot is shown macro and macro cluster, and the second plot is the summary of the day instead of we use table for the previous experiment. DSAP found dense macro cluster centroids in the indoor space 400, 500, and 659. Also, it found cluster around a space 300, 400, 70, and also here 700. I should mention that X and Y are not the same scale. That's why the branches might seem that they are far, but actually they are in the similar indoor spaces. In rapidly changing data like this, the choice of expiration time is critical to interpret the data meaningfully. And these 4 plots are clustering results for entire experiments during 6 days across the 3 buildings with the value 20,000, 2,000, and 1,000 and 200. The first figure showed the cluster of for almost the entire data using the expiration value of 20,000 in each of these 3 buildings. The first 5 days of data were collected, which I mentioned from the first building. As we decrease the expiration value from 20,000 to 200, the occupancy behavior start reflecting more on the current data. And gradually building 1 fades out from here, which fade out with the actually lower expiration time since no measurements were made in this building in the later days. Just like what we did with the encounter data, we use the AP model as a baseline to compare the performance and validation metrics for occupancy behavior experiment. June 20 was selected for this evaluation. Results show that a similar trend showing that significantly decrease in memory consumption and processing time. And the 3 indices that are used to evaluate the cluster show that macrocluster generated by DSAP has a satisfactory value. To sum up, a new data stream clustering AP algorithm is proposed for finding evolutionary pattern. The DSAP algorithm is more efficient in terms of memory consumption and processing time as compared with AP. The quality of cluster generated by AP also consistently better. For the first experiment, motivational intervention on the physical activity of people was analyzed, and the impact of this intervention wasn't clear, although a slight increase in stair usage was observed. The second experiment was used to find the occupancy behavior in these 3 buildings, and these results show the ability of this algorithm to capture the changes in occupancy behavior. This algorithm has some advantages. Most importantly, less processing time using landmark time window. The quality of clusters are good, and it is applicable to other indoor space systems. And it has some limitation, like we haven't tested on using with live data stream, and we haven't tested the bandwidth and latency problems. The future work will be such as using the multiple distance function depending on the data distribution and shape of the clusters. Different time window models are applicable, and the performance of the DSAP should be tested by live stream. Also explore the effect of noise on the performance of DSAP. And finally, benchmarking tests to evaluate the DSAP model with the existing AP models using a standard dataset. Thank you all for listening. This is the end of my presentation.
Thank you very much, Nasrin.
Thank you.
There was something that I had forgot to do at the beginning, and that was to introduce the Board of Examiners. So I'll do that now before we go to the questioning period. Your supervisor was Monica Vashowitz, and the other members of the examining board are Ian Church from Geodesy and Geomatics Engineering, and Sakib Hakak from the Faculty of Computer Science. So now we will move to the questioning period, and I will ask each member of the examining board to ask 3 questions over a period of about 15 minutes or so. And when we conclude the first round of questions, we'll go to a second round for 1 or 2 additional questions from each of the examiners. Now, as Monica was unable to be with us this morning, she has sent me her questions, and so I will ask the questions on her behalf. Okay. Okay. So Nasrin, Monica's first question is this. You have explored the DSAP model using the most popular types of indoor localization technologies, that is Wi-Fi and E-counters. However, there are other technologies available. Could you provide other examples of indoor localization technologies being used today? Could the DSAP, and it's a multi-part question, could the DSAP model be also used to find clusters from data being generated using these technologies? And would you have to make any changes to your procedure if using one of these other technologies? So it's kind of 3 questions in one.
Yeah, yeah, it's a long question actually. Yeah, I should mention, yeah, in this technology actually nowadays is more popular for indoor spaces, as we know that GPS is not very good experiment for indoor spaces because of the signal, and it's weak for inside. And then different technologies are like using infrared sensors, using Bluetooth, using ultrasonic